Tolerances are important because they dictate a lot about how your designs will interact with individual parts of the design or other things in their environment or manufacturing cost and lots of other things. So tolerances at the very basic level determine how close duplicate parts are to being perfect copies of each other. And they dictate how parts either fit together or don't fit together. And they also dictate how much your parts cost, how much your design might cost to manufacture in small quantities or large quantities, or over the course of some period of time. And tolerances rely on a lot of things. They rely on the repeatability of the tools and methods that you're using to make the parts. That's to say, it matters how close a particular machine goes back to the same point one time after another, or how close a piece of raw material is to the previous piece of raw material. They're dictated by a lot of nonlinear behavior, such as if you move a particular process faster or push harder on something, it might behave differently. That can affect the tolerances. How much parts of the process are worn will dictate the tolerance. If you've ever tried to cut something with a dull knife, it cuts very different than with a sharp knife. How rigid or floppy parts of the setup or the process are. Temperature can affect tolerances, and operators can affect tolerances. Different people can achieve different levels of precision using the same tools depending on their technique and experience and things like that. So I'm going to start looking at the drawings for the hammer that we would explore. And there's two different basic types of tolerance that are shown on this drawing, and they're implicit tolerances and they're explicit tolerances. So the explicit tolerances are the ones like here, where you have a specific window where the basic dimension is allowed to deviate in either one direction or two directions. So underneath I've written this basic dimension of 0.500 is allowed to be 1,000th larger, but no smaller than this dimension, giving those bounds. Other places on drawings you'll see here where there's not an explicit dimension printed on the drawing. That's something that you would reference in the tolerance block at the bottom of the drawing, which gives the implied tolerances for example, these 2-digit numbers have a tolerance in the tolerance block of plus or minus 30 thousandths of an inch. So on this drawing, I've marked in what those actually translate to that are given down here, because this is a drawing that I would use in the shop, and I want to easily be able to remind myself which one I have to pay attention to. So when you're in the shop or you're working on something, writing all over a drawing is a really good way to keep track of those things. And that's something that we encourage. Make it really easy for yourself to keep track of those. So in addition to just saying what the dimensions are, these individual tolerance amounts will dictate how your parts might have to be made, because different techniques have different tolerance windows that they can accommodate. So I'm going to put these charts available so that you can see. So things that you would see in the machine shop are generally in this category, and you can look up in lots of different charts the different grades for what that tolerance will provide. So the rougher or lower tolerance methods are to the right, and the tighter and more precise tolerance methods are to the left. So to the right, the ones that we would be generally exposed to in the machine shop are things like using the milling machine. Turning refers to using a lathe. Reaming is sort of a precision drill bit. And you'll notice that all of these things give a range of the tolerance that those particular methods might be able to accomplish. And I really like this chart in particular. This is color-coded to the grades that were up on top. This chart shows you how the tolerance might change for something of a different nominal size. So one particular machine might be able to hold 1,000th of an inch tolerance on a small part, but when you start making a really, really large part, holding 1,000th of an inch tolerance over a part that's several inches long or tens of inches long is very different than holding a small tolerance over a part that's very, very small. So that's an important thing to keep in mind. And why that's important is because maintaining tighter tolerances as you go up the chart for parts that are larger is more difficult and dictates that you have to use more precise methods. And it also dictates that your parts then become usually much more expensive. You can directly correlate tighter tolerances to more expensive parts. So looking at these drawings, I have two drawings for the hammer here, and just making the parts within some dimension is the first part of tolerance, and then how the parts actually fit together is the other part. So in the hammer project, we have two parts that have to fit together in such a way that they won't actually come apart. They get forced together. And those two parts are where this portion of the head is supposed to get made so that this pin is larger than the hole that it goes into, and we have to actually force them together using a press tool in the shop so that they won't come apart. So in a complete one, when it's put together, this portion shouldn't be removable. It should be permanently attached. And the way that that's shown on the drawings are in these two red boxes. So in the bottom, I have the pin, which is this diameter, which is dictated by this dimension here. So the basic dimension for the size of this pin is 0.502, and it's allowed to be no larger, but a little bit smaller. And then here I've notated what those dimensions actually are. It should be 0.5015 to 0.5020. The hole, which should be a little smaller, can only be 0.500 plus 0.1, but not any smaller than 0.500. So when you subtract those two allowable sizes from each other, it gives a guaranteed interference fit of 5/10,000ths of an inch up to 2/1000ths of an inch on the large side. So if both of these parts are made according to this drawing, the tolerances guarantee that the pin is always a little bit bigger than the hole, even if both of them are at one extreme or another. And that's really important because for something like this demo piece, we changed the tolerances a little bit to make sure that they fit together snugly, but still allow me to remove them by hand for a demonstration. Same thing for this demonstration piece. I want to be able to remove this, but still have it be a tight enough fit that I don't lose one or the other. And in the finished one, specifying the fits like that allows you to permanently attach the two pieces of each other so that they don't ever come apart. So again, a graphical way to look at this is the red colored bands on the left are the tolerance. This is your pin. This is the hole. So the pin is allowed to have some variance and the hole is allowed to have some variance. And in this one, specifying that it's a clearance fit, which is what we did for the clear one and for the cutaway, we have to guarantee that the tolerance that the machine will produce for both of those parts exists such that when I've made both of those parts, there's still a little bit of a gap in the middle. For the real part, where we're making an interference fit, where the parts actually overlap each other, you can see that the red portions always overlap more than the amount that they would go together, which guarantees that at the smallest and largest sizes of both of those parts, they will go together. So the last comment that I have to make about tolerances as you go through your manufacturing is that tolerances generally are given as some range of either the particular process or machine will have a range of some amount that it can produce, and that's usually the bounds of the range. So like a lot of things in the sciences, tolerances can be really adequately described by a normal distribution with some number of standard deviations dictating where the parts lie. So even if your machine says it's capable, in this case, in this drawing, we're looking for a nominal dimension of 1, and then we're rejecting parts that are larger or smaller than 15/1000ths larger than 1 and 15/1000ths smaller than 1. Those are parts that lie outside of what we're allowed to do. But what the machine and the operator actually produce is most of the parts are pretty close to the nominal, and then some of the parts will fall outside and maybe as things particularly wear out or some other condition causes the parts to go outside of that range is where you might not have acceptable parts anymore. So when you're going through your lab activity and you've measured duplicates of whatever you've been able to get to in your place of residence, when you're going to design the holder or the thing that that those pieces interface with, give yourself a little bit of buffer room about if you didn't happen to measure the absolute largest part in that distribution or the smallest part in that distribution, make sure that you design your part in such a way that all of the possible ones that you might encounter would actually fit into that part. And then when we get into later sessions and you get into the machine shop and we get into parts that have to be forced together and not come apart, you just apply the inverse. So the principle is the same. The execution is a little bit different. And there's a little bit more to get into for tolerances. And that's what we want you to get out of this one.